Good afternoon, everyone. Thank you so much for coming to the IAD's Distinguished Speaker Series. And my name is Deming Chen, and I'm the director of the IAD. And I know today is a snowy day, and thank you so much for coming, and also especially our distinguished guest, and Professor Deming Chen from University of Illinois, Urbana-Champaign. I don't have to read any bios, because I know him so well. I can just tell you. And actually, Deming and I had an overlap at UCLA, and he was a year ahead of me. And after graduation in 2005, he joined Illinois and become an assistant professor. And his advisor is the famous Professor Jason Kang, but he also worked in the FPGA, but he quickly established himself, as the leader in this FPGA acceleration and verification and synthesis. And now he's endowed professor at Illinois, and also the director of IBM Illinois Institute for Accelerator Discovery. And he has a lot of best papers and a lot of very, very well-cited work. And he's also actually established a very good collaboration with the industry. Besides IBM now, he also directs the Illinois and with AMD, right? Mm-hmm. And the Xilinx before, and for the big advanced computing centers as well. So great accomplishment. And so we are so happy to have him. And we welcome him with a big snow, and he probably brought snow from Chicago to us as well. He arrived actually last night at 2 a.m. And stayed the whole day probably in Chicago airport. So thank you so much for taking the time to come here and share about his work, and looking forward to it.
Please. Thank you very much. All right. So yeah, it's my great pleasure to be here. Right. So this is probably the third time for me to visit Buffalo, but the first time to visit this university, right? It's a beautiful campus, right? And so today I'm going to share some works we have done in terms of AI algorithm accelerator co-design, co-search, and co-generation, okay? And actually some of this work or through close collaboration with Jing, right? So when Jing was in the industry, right, as a director, right, at IBM, Jing and the faculty member of UIUC, Wenmei Hu, co-directed the center, right, C3SR center, right? So that center actually made a lot of impact and supported quite some smart and hardworking students and postdocs. And so a lot of ideas actually originated during that period at the time, okay? All right, so then here is the outline, right? The motivation, the A3C3 method, and then A3C3 based solutions won some AI competition awards. And then we further take that idea into kind of a more systematic approach. We call it EDD, Efficient Differentiable DNA Architecture Implementation Co-search. And then this idea is extended into large language models. So the large language model-based works are more recent. And then I will conclude this talk, right? So if we look at the traditional top-down deep neural work design, a deep neural network design and deployment, right? So typically we'll have the software design iterations, right? So people who work on AI, right, are familiar with this process, right? And then including some software-related optimizations. And then after that, in order to deploy such deep neural network, for example, onto edge devices, right? So the edge AI is really becoming so important these days. Then we have to consider hardware-related optimizations as well, okay? So then if we look at this top-down DNA design deployment, right, we immediately see some drawbacks, right? So first of all, the software metric, hardware metric, sometimes they do not really, talking with a common language, okay? And then a lot of times it's difficult to select a proper reference DNS, and many times it's almost like a dark magic, right? It's more like a try and error kind of approach, right? Okay, so then if you look at this whole thing, right? So sulfur DNA model, right? We need to have an iterative process, and you are happy. Oh, this is perfect model. But then when you try to map to the hardware, you realize, oh, either it's too slow or it's too kind of power hungry, right? Or it's not so efficient, right? And hardware utilization is not good, right? So then you have the hardware accelerator design, and then it's doubly kind of loop kind of design methodology. And then typically we cannot really achieve optimal solution, right? Okay, so when we look at this, right, so then we start, can we, start from scratch when we design the deep neural algorithm and its accelerator, can we put them together right at the beginning? So they are friends and they are growing together, okay? So that's the idea we came up with, right? So both the AI algorithm accelerator design space are parameterized, right? Because we have a software design space, we have a hardware design space. When we combine, there's a combined space, right? And then typically that space becomes much bigger, but then how do we effectively search that combined space, right? There are different approaches, and one approach is through gradient descent, but typically for hardware design, it's discrete, right? So how do you make it converted into continuous so then it become differentiable? That's part of the challenge. But then I'll talk about that later on. However, so just based on this picture, you can see we have the algorithm design, right? They look like deep neural networks, okay? By the way, this is color coded, okay? And then while the DNA is evolving, okay? And then the hardware is evolved together with the software, okay? And then, so if we are using okay, so this is, okay, so if we are using this overall iterative design approach, you can see the deep neural model, DNA model, and the hardware accelerator are designed together, and they are improving together. So when you eventually converge, you have both the algorithm and the hardware, right, produced, right? So that's the idea. And then if we take a co-design kind of approach, then you have the DNA model on the top, hardware accelerator on the bottom, and then you become a bidirectional. Okay, so then we actually proposed this idea about 7 years ago. Okay, so we are among the first to produce, propose such a co-design idea, right? And then this is a conceptual kind of white paper, right? And then we have inputs, right? We have target applications, around 2018, it's a deep neural network for image, object detection, and those things, right? Facial detection, those things are the most popular, right? And then go through the co-design engine, then we can come up with different solutions, and the solutions will contain both DNA models and their corresponding implementations, right? So then to shorten the DNA development time by avoiding the tedious iterations. So that's the conceptual idea we proposed. And then 1 year later, we kind of materialized this idea through a real implementation, right? So actually, the lead author was Kathy Hall, right? Right now, she's an assistant professor at Georgia Tech, and she was founded by this C3SR center that I mentioned at the beginning, and Jinjun and I kind of co-advised her, right? So to come up with the idea. And then you can see the whole thing is automated, right? So we have the co-design flow inputs, and then we have this interesting kind of bundle architecture because deep neural network is kind of regular, right? So you have the layers, and typically you stack the layers, right? So even for the large language model, right? So you have a decoder layer, right? So then you just stack them, right? And a lot of times they look alike, so then we can use them as building blocks. And then we have this auto DNN based on using those building blocks to automatically stack them, right? Trying to achieve the desirable accuracy. And then based on this building block, we have corresponding hardware implementation. And the hardware implementation is through a hello census flow, right? So hello census flow, that means we can describe the hardware from a higher level description language and using a tile architecture. And then you can see the deep neural network is trained, and then we produce the software hardware together, right? So this is the first kind of complete flow that can produce the real solution, okay? And then let's quickly introduce this bundle, some details, right? So this bundle become the connector, right? Mediator between the software and the hardware, right? So here is one example of the bundle, right? So here it's mainly for image-oriented, computer vision-oriented applications, right? You can see the bundle is lightweight, okay? And then we want to make sure this is suitable for edge, computing. And then when we do DNN kind of design space exploration, it's more like you stack these bundles, but then you can expand some channels, you can expand some pooling and things like that, right? So I have more details later on. And then each of the bundle can be have a corresponding hardware, right? So then while we are exploring the DNN design, the hardware design is also built along the way, okay? So with this idea, we continue this study, right? So actually around 2019 and 2020, we use this method to join a system, kind of system competition. It's a very, very competitive, right? It's a DAC system design competition. And then, so this just, take one step further. It's more scalable than the previous work I introduced, right? Then we can evaluate the bundle. Then we can build a Pareto curve, right? The Pareto curve is typically the trade-off between the latency and the accuracy, right? So then it really depends on your design target, right? So if you're willing to pay more in terms of resource, then typically the hardware can run much faster, right? And then if your model can become bigger, and typically it's more accurate, right? So there's a trade-off there. And then we have this PSO, that's a so-called particle swamp optimization, right? It's one variant of evolutional algorithm that consider both local optimality and global optimality. And then you can see we can automatically stack the bundles. And then there are some other hyperparameters, right? So channel expansion or pooling positions, right? And go through the design space exploration. And then after that, we can have some fine tuning. So then we have the system level design, right? So we come up with a pipelined accelerator, right? Dedicated to run the bundle, right? And I will skip the details. And with this design, we joined this DAC SDC competition. It actually use single object detection for real life UAV applications, right? And then images contain 95 categories of target objects. Most of them are very small. And then the comprehensive evaluation accuracy throughput energy consumption. So here we did some analysis, right? So this is a distribution of area output box. That's the small object we need to detect over area of input image, right? So you can say 30% of the target object is only 1% of the input size, very tiny, right? And then 91% less than 9% of input size. So I have some examples here. So these are the real images, videos that we use for this competition, right? So can you tell what's the object in the middle? It's actually a person riding a horse there, okay? And so here is the, we call the Skynet, right? Based on this A3C3 design methodology, right? And you can see, so those are the bundles, right? In the dash box, that's the bundle. And then we have the channel expansion, right? And then we also have some shortcut features, right, coming out of this design methodology. And then we also have the system level design, right, CPU. So there are two types of target hardware, GPU or FPGA, right? So we have a ScanNet as the brain of this whole thing, and then evaluate the final accuracy and speed and energy, right? So here are some, results. We actually won the championship for both the GPU and the FPGA. So for the GPU, we use this TX2 GPU, okay, from NVIDIA. And then you can see compared to the second place winner, we are 2.3x faster with the similar accuracy. Okay? And then with FPGA, we actually similar speed, but 10% more accurate, right? So this really demonstrates when at the beginning you design the algorithm accelerator together, when they fully agree with, when they work as a team, it's much more powerful, right? So these are just quite natural, and then we expand this into some other domains, right? So this second demo is generic object tracking in the wild. Okay, so then we extend SkyNet to real-time tracking problem, right? Use the large-scale, high diversity benchmark. Okay, actually has 1.5 million labeled bounding boxes, and so tracking is different, right? So then you can see the size can change, the speed can change, the direction can change, right? But then typically they have a model, like a detecting model as a backbone, right, to do this object tracking. So how do we really evaluate the accuracy? What we did is we take some popular framework for object tracking, and then typically they use a backbone deep neural network, right? And for example, if we compare to the previous backbone, right, the ResNet 50 is a very popular backbone, and replace that backbone with ScanNet, right? And then we evaluate on average overlap, that this is more like an accuracy metric, and the success rate, right, defined as a proportion of predictions, where the IOU, right, the IOU is more like overlapping, right? So your detected bounding box and the ground truth bounding box, how much they overlap, right? So beyond the, so for the success rate, it's beyond 50% or beyond 75%. And overall, we have similar AO by 1.6 faster versus ResNet. And then with another framework, right? So we are 70% faster, right? So this demonstrating that the model, right, coming out of this coding method is quite capable, right? Not just for typically like an edge AI implementation, but then as a backbone to enable some other applications. So any questions so far? Okay, if not, then let's move on. So further improve, right? So for this SkyNet work, right, DNN is accelerator search coordinately, right? So I just gave a very quick introduction, right? So hopefully that methodology makes sense to you. But then we asked whether there's a more elegant way for co-design space formation and the search, right? At the beginning I mentioned, can we, for example, have a more systematic way, like a gradient descent, to search the space more thoroughly? And considering that gradient descent is very effective, right? So if we can come up with a gradient descent way to search this kind of co-space, right? So this merged space, that will be quite important. Okay, so then we look into this work, right? We call the EDD, and so actually there are some previous work that's doing neural architecture search, right? So-called machine learning, right? So I will present some results later on. Some machine learning automated searched models can outperform human designed models. Okay, so then our goal is to have the hardware considered into the neural architecture search, right? So then again, we produce models that are very hardware friendly and that can beat the existing machine learning search solutions. Okay, so then here we just demonstrate we have this merged design space, right? And then we will formulate not just the neural architecture, but also its implementation as differentiable, okay, and then solve it through gradient descent, right? So if you look at this, so here is our proposed co-design formulation. So it has 3 parts, right? So for the first part, for the A part, is similar to some existing neural architecture search idea, okay? But then we have this additional I part, right? So Illinois is orange, right? So if you visited Illinois before, right, orange is our color. I also represent Illinois here, so that's why it's orange, okay? Yeah, and so here, the idea is the implementation I should be also variable. And then the challenge is how do we make that variable differentiable, right? So if we can solve that, then we can use gradient descent for this merged space, okay? All right, so here, just some high-level description, right? So I have no time to go through the details. Let me introduce how the differentiable neural architecture search can work, right? So if you have looked into this particular domain, right? So there's this SuperNet-based neural architecture search where you have a template, right? The template is just block by block stacked together. That's like the bundle idea I introduced before, okay? And then they need to search the internal structure of each block, right? So how do they really search? You can see this is one block, right? If we zoom in, it has n options, okay? And then the search algorithm need to determine for this particular block, which option I should pick that can really maximize my accuracy, right? So for deep neural architecture search, and then here within this particular operation, then it's like a bundle. It's like the bundle structure I introduced, right? So then the trick that people use is so-called gumbo softmax. Okay, it's kind of going through a sampling process and then go through a softmax, we know, right? For softmax, you can convert a bunch of values into a distribution, into a probability, right? And then the summation of the probability is equal to 1, right? So then you go through this kind of sampling process and convert the discrete option into a distribution kind of option. Now, of course, based on that distribution, the best options is embedded, encoded into that distribution. And that distribution is differentiable, okay? So that's how people use this kind of SuperNet-based differentiable neural architecture search idea. And then immediately we can extend it into hardware design. So how do we do it? Now, for hardware, what are hardware specific? For example, quantization is a hardware specific topic. Or parallelization factor, right? It's hardware specific. But all these are discrete, right? So then we can do the similar thing. We can do a gumbo softmax sampling, right? And then this become the first level, the hardware level. And then we combine the hardware level search together with the software level search, okay? And then the whole thing is modeled through the same formulation. And then when we do the gradient descent, then both the hardware parameters, for example, the quantization bit width or the parallelization factor numbers, and the specific neural architecture on top of these hardware features are all searched together, right? So hope you see that, right? So, so then we just feel, oh, this is much more systematic, much more elegant than the previous kind of study, right? So I'll skip the details, and then based on this, we searched and produced 3 networks. We called it EDD, Net 1, 2, 3, right? So not a fancy name, right? So, and then we'll compare for the EDD Net 1. So as I mentioned at the beginning, right, so we have these human designed models, GoogleNet, MobileNet, right, so very kind of famous, popular. And then we also have machine learning searched neural architecture, right, and probably less known, okay? But then you can see they actually have better accuracy compared to the human designed models. Okay, and then our EDD net 1, right? Because again, right, the model and the hardware are co-searched, co-designed, and then we maintain similar, right? So here, this is our accuracy. It's kind of similar in the same kind of magnitude in terms of accuracy, but then we are much faster, right? So this is similar to the data we presented for that competition, right? So we maintain similar accuracy, but much faster. And then because it's a search algorithm, then we can produce different type of models, right? So for this second model, we target recursive FPGA. That means it's more like an NPU, right? So you have this hardware architecture, right? And then because the layers are kind of similar, like a TPU, right? So you have this systolic array designed. Then you have one layer run on top of systolic array, produce intermediate result, then come back and feed into the same systolic array again and again, right? So that's called recursive FPGA, and we can produce that. And then, so here it's a similar story like this GPU, right? So here, because GPU is like you have a phased architecture, and then you just reuse the architecture again and again, right? So then we demonstrate advantage in terms of latency as well. Okay, and then we can also produce dedicated FPGA accelerator. So for this one, it's like, let's say we have 10 layers in this model, okay, and then we can map all the 10 layers to FPGA, okay, and then we can enable data flow architecture, okay. So once the intermediate result of first layer, once part of the result is produced, instead of writing it out to the memory and reading it back, we can pass to the next layer immediately, right? So it's a data flow, right? So because of data flow, we can significantly reduce the overall latency. So previously, we published so-called DN Builder, okay? And I think Jingjun also part of it. This DN Builder won Best Paper Award 7 years ago. And then our EDD Net 3 is not as famous as DN Builder, but actually beat DN Builder, right? So then this, for the students in the audience, it's important to reach there for the first time, okay? That become quite important. And then later on, people, of course, can outperform and all that, but people always remember, oh, this is the first work that reached that idea, right? So yeah, so then this actually demonstrate again, right? So hardware, software. Here is a particular AI algorithm, accelerator, co-design, co-search, co-generation, right? The co-generation part is important because we want to automate the whole process. Yeah, become essential when we're moving forward, especially for AI on the edge. Okay, so any questions before we move on? All right, if not, we can move on, okay? So I think, I'm good with time, yeah. So how about large language models? So currently, this is a crown jewel, okay? And then how do we really apply this methodology for large language models? And we know for large language models, we have limited hardware flexibility, right? So typically just GPUs, right? Run on top of GPUs. Or TPUs, right? These are fixed architecture, right? So then the idea I present here is kind of inspired by A3C3. That means we really need to consider the hardware constraint when we design the large language model, right? In order to improve its overall speed, okay? But then potentially, this, hopefully, right, this kind of study can also inspire the architecture design, right, to make architecture more algorithm friendly or make the architecture more configurable. So I think there are some AI startups. They start to consider at least some coarse grain reconfiguration for AI accelerators, right? So that can be more adaptive to emerging AI algorithm, right? Otherwise, you have a new AI algorithm coming in, right? They grow very quickly. And then you are optimizing your hardware is optimizing for the model that's 1 year already, it's 1 year old, right? So, hopefully this kind of study can inspire us to consider both algorithm and hardware, and then co-design them, and then hopefully, right, so then produce much better models and much better hardware that they can work together. Okay, so here probably you have seen this chart, right? And right, so this is this famous paper, right? All you need is attention, right? Or attention is all you need. Okay, and I think it's almost like 300,000 citations, right, for this paper. I didn't check the most recent. And then you can see, right, the speed up, right? So this is exponential, and this is even faster than Moore's law, right? And for example, if we just use a GPT as example, right? So between GPT-3 and GPT-2, the jump is more than 100x, right? And then, of course, we have there GPT-4, the jump is about 10x. And then people predict GPT-5 actually is more than 10 trillion, but of course, it's an MOE kind of architecture, which makes sense as well, right? Because if it's otherwise, it's just too huge, too costly, right? So MOE makes sense. It's just like our brain, right? We have different regions that specialize in different functionality, right? Okay. So with such quick growth, and then we are indeed facing some challenges, right? And then so, right, so 10 to 20x increase of RM size per year, and the rising size of model itself input also introduces huge parameters, key value caches, right? And then make the RM inference latency, a very big challenge, and especially the inferencing will be running much longer than the training, right? If we think training is costly, is power hungry, let's say you train a model in 6 months. However, when you running the inferencing, right, so millions of people running it every day, right, and then that can be much more power hungry. And then the inferencing part, how do we really effectively use the hardware, become quite important. Okay, so then our inference predominantly memory bandwidth bound, right? This is because, for example, during the kind of forward pass, right, it requires all the parameter loaded, right? It can be billions of parameters, and then this KV cache can grow very rapidly. I have some statistics to show that, pretty soon. And making decoding memory intensive, hard to parallelize, and then it typically underutilize the hardware available to you, right? Think about the GPUs advance, right? The hardware also advance very quickly, right? It becomes so powerful, thousands of cores, right? And but maybe you only use 20% of them, right? So then that's a huge waste, okay? And then, so then our question, how to make large language model hardware aware for higher performance, particularly 2 questions, given all the model parameters available, can we produce more useful results each time? Just very natural, this question just come out very naturally. How do we effectively compress KV caches without compressing quality, right? So, so for the remaining time, I'll present 2 pieces of work that try to answer these 2 questions, okay? All right. So for the first one is called Medusa. So anyone knows about Medusa work? Okay, all right, thank you. Okay, and when you look at that picture, right, of course, Medusa is like a mythical kind of feature, right? And but we beautify the Medusa headshot, and then you can see our logo is like a Medusa, but replaced with a llama, right? Okay. Now, of course, llama is pretty famous for large language model. Okay. So what's the fundamental idea? So typically, a large language model only have one head, right, to produce token by token, right? Each iteration you produce one token, right? So then what we do is, given that the hardware is available, right, and the single token will heavily underutilize the hardware, how about we produce more heads, right, and producing more tokens, okay? And then the idea is we will produce the tokens, more tokens in parallel. And then if we have a good kind of strategy, let's say each cycle we produce 5 tokens instead of 1 token, right? And then if we have a good strategy to producing such tokens, let's say if out of the 5 tokens, 4 of them are good tokens, then you accept them right away, right? You know, single cycle you accept 4, then you have 4x speed up compared to the original, right? So it's a simple idea, right? And then we designed it, okay? So then you can see we call it Medusa head 1, 2, 3. And then during inference, each head generates multiple top predictions for its designated position, right? So this is a common, right? So even for the single token generation, you'll produce multiple possibilities, and then you pick the best one, right? So then here, for this example, we have 3 more heads, okay? And in the actual Medusa implementation, we have 5 heads, okay? So, but here we have 3 heads, and then in its corresponding position, we have the top options predicted, okay? And then this just become like a tree, right? So if you study algorithm, you know, right? So it's like a tree, and then you have multiple options. For example, it is difficult not, or it prime difficult, right? So you have different options now, right? And then the idea is, how do you quickly pick the most probable path in that tree, and then you verify that tree, and hopefully out of the 5 tokens produced in parallel, you accept as many as possible, right? So that's the fundamental idea, right? So once you get the idea, you know what Medusa is doing. So nonetheless, right, it just mitigate the compute resource underutilization problem. So let's say originally you only use 15% of the GPU. Now you use 15 times 5% of GPU, right? So then to just naturally speed up the whole thing. So I don't need to go through all these details, but this is the tree that I talk about, right? And then we'll pick the most probable tree branch out of this verification tree, and then do the verification, right? So and then eventually we can guarantee the accuracy that way, right? So let me introduce some results. So we have 2 types of Medusa. The first one is fine-tuning Medusa heads. So just fine-tune the heads itself, right? So then you can see this requires much less computation resource. Another one is you jointly fine-tune the Medusa heads with the LLM backbone, right? So then this is more, how to say, create more harmony between these heads, right? Because, you know, think about it, it becomes a little bit like a monster, right? Originally, each of us only 1 head, right? Now you add additional heads, right? So how they do not argue with each other, right? Need to create a harmony, and then it's basically the Medusa heads fine-tuned with the original large language backbone. And then very naturally, you know, then this one is a Medusa 2, right? Of course, Medusa 2 has higher speed up compared to Medusa 1, right? Then this can across different models. And then for this one, this is like the roofline model, right? So if you read the TPU paper, you will see this kind of roofline model. So there's a computation roof, that's the red line, and that's a memory bandwidth roof, that's the blue line, right? So we run this on A100. So the blue line is the memory bandwidth. It's 1.9 TB per second, right? And then the computation roof is 300 T-flops per second, right? So without Medusa, we are talking about this particular gray dots, right? It is under the memory bandwidth. Remember, this is memory bandwidth bottlenecked, right? So you cannot really go beyond the memory bandwidth. But then it's pretty low there. But with Medusa, especially when our tree becomes bigger, that means you have more heads, then you go really up towards the more performance region. Okay, all right. And then here is a demo, right? Without Medusa, with Medusa, similar quality, but much faster. Okay, so this is open source, and actually it's adopted by quite a few companies, including NVIDIA, right? So NVIDIA wrote a blog, right, about this, and then they actually run Llama, right? Good, right? They run on top of Llama, and they even run on top of 405B, right? This is a Medusa 1, right? Because it will be very expensive if you fine-tune the 405B again, right? So the 405B or 70B is frozen, just fine-tune the Medusa head, and then they achieve up to 90% improvement in terms of overall performance. Any questions on this? Let me drink some water first.
This is already have close to 500 citation.
Oh, this one. Okay, all right. What's the citation for the, all you need is attention?
20,000.
200,000. 261,000. Okay, all right.
So you need to be the first.
That's right. Okay. Okay, I'm good with time. Now, let's talk about KV cache compression. This is another huge challenge. Okay. So, so if you look at this curve, right, the sequence length is the prompt, right? So you need to ask large language model some questions, and these days the prompt can become very long, right? For example, you can ask large language model to read some kind of long report, then give you all kinds of summary, right? And then think about the article can be very long, right? And then here, we just talk about 8,000 tokens, okay? And then the KV cache is already 30 gigabyte, right? And then think about what's the memory for GPU. Typically, you have 80 gigabyte or something like that, right? So this quickly go out of control, right? And then we also did some study here, right? So we have the prompting latency, that's the blue bar, and then the generation latency, right? Prompting, you have the prefill phase, that's the phase it generates the first token, right? And then you compute all the KVs and all that. And then typically people just save the KV, then become a KV cache for the generation stage, where instead of recomputing KV, you just kind of check, right? It's like a cache, right? You check whether the KV are there, and then just read it, right? So without snap KV, right? So this is snap KV, that's our idea. Then you can see the generation latency can be much longer than the prompting. Okay? So then this is the motivation. How do we really compress the KV? Right? It's like a cache compression. Save the most frequently used KVs in the KV cache. Throw the others away. Right? So of course, there are other people. Many people are working in this domain. For us, we just prune away the useless tokens. For others, maybe they have a hierarchical cache, right? For the not so useful, not so frequently used KVs, they downgrade it into, for example, CPU memory, because CPU memory sometimes can be much bigger. They can even downgrade down to SSD, right? And then once you use it, you have to load it, right? But then it just has a fairly the overhead, right? So for us, for this particular case, we just identify how do we really identify the most important KV values and only store those. For the rest, we just prune them away, right? So that's the key idea here. So how do we do it? Our solution is called snap KV. So let's say you have this prompt, right? And then, help me analyze the Q4 report of this company, right? And then can you tell me the details of, right? So that's just typical prompt, okay? And then what we do is we look at the input sequence KVs, okay? And then we divide it into prefix region and observation window region. I will introduce the detail pretty soon. Again, the idea is actually quite simple, okay? And then based on the observation window, we find out the one region, through this whole prompt. One particular region is very important that can capture the most important attentions, okay? And because attention is all you need, right? So we need to pay attention to attention, right? So then here, let's see, we find out, oh, those orange, right? You probably already can tell we love orange. Right? Orange is our favorite color, right, in Illinois. Okay. So based on the observation window, we identify the most important tokens, right? Then they are orange, compress them, snap, right? Take a snap. That's why we call it snap KV. And then you can see this compressed KV is much, much shorter than the original KV, right? And then the question is, how do we really capture the most important tokens, and then whether it will degrade the quality, the final quality or not, right? So then here in summary, right? So phantom-free with minimal model modification, achieve a consistent decoding speed with a 3.6x increase in generation speed, achieve 8.x enhancement in KV cache efficiency, and we test this result across 16 data sets, okay? And then this, we can process up to 380K contact token on single A100 80 GB GPU, okay? All right, so then let's find out how do we identify this so-called observation window. Okay, so this is an important study. So we divide prompt tokens into non-overlapped windows. So here we have this example, we have 20 windows, right? So you have the prompt, just divide into 20 windows, non-overlapping. And then for each prompt window, we calculate the attention between the window and all prompt tokens, right? So it's just profiling, just like exhaustive kind of profiling, okay? Then critical token, the token with high attention rate. For each window, we measure the overlap between the critical tokens identified by this window and the actual critical token identified by generation, right? During the generation, of course, you will use the most important tokens to produce the next token, right? So that's the ground truth, right? So then we will measure the overlap between the critical token identified by this window and the actual critical token, right? So then we observe that the last window could identify the imported token used in generation. So this picture demonstrates that, right? Each line represents a model layer, right? So then, how many layers? I didn't really count, maybe 30 layers here, 30 lines, right? And then we have 20 tokens, 20 windows, and then the most overlapping, right, between the critical token is the last window there, okay? So then we just, for the last window, we call it observation window, okay? And then based on that observation window, we calculate the most important tokens has the highest attention and only keep those tokens, compress them together and throw away the rest of the tokens, right? So this is just to just illustrate the idea, right? To elaborate a little bit more, right? To demonstrate indeed, right? So through this is a matrix multiplication, right? And to demonstrate the idea, okay? And so here, additional data, okay? So we divide 512 generated tokens. So this is in the generation stage into 4 non-overlap generation windows, okay? And for each generation window, we calculate the overlap rate between its selected critical token and the MOBS, right? That's the critical token selected by the observation window. And then here are 4 windows. Then you can see the behavior pretty much match, right? So whether, for the entire generation, okay, for here we divide into 4, and for each sub kind of generation region, the most important tokens match. They are heavily overlapping with the tokens identified by that observation window, right? Okay, and then we did some other studies, right? So here this is invariance to instruction position. Remember, we at the beginning we have the prompt that has question, whether the question is beginning, in the middle, in the kind of end, that doesn't matter, right? So this pattern is consistent, okay? But then if the questions are different, then they do not match. This is also a good indication that when we are producing this snapshot, it has to be dynamic. It has to be instruction specific, right? So then the previous kind of static compression method will fall apart. But for us, it can be tailored towards different data sets, tailored towards different instructions, right? So this methodology is good, right? Across different instructions, across different data sets. Okay, so then just very quickly, so how do we do it? So we split the observation window, right? So there's a prefix observation, and then we calculate the attention between prefix observation window, right? And then vote to select most important tokens, okay? And then after the most important token is selected, we do some pooling that can consider some local kind of token as well, right? Typically, you have important token, then you have to grab some local neighbor tokens to make sure it has a good context and good meaning. And concatenate, select tokens, and then generate with compressed KV, right? So again, very simple. So then let's look at some results. So this one is decoding speed and memory bound, right? With this particular benchmark, right? It can go up to 1 million, right? Tokens. And so then here we go through up to 262K input length. And then if we look at the sequence length of 16K, that's this line, right? Some KV optimum model achieve a 3.6x speed up. So this is the square, right? And compared to a green square up there, that's the without the stamp KV, indeed, right? So we are 3.6x faster, okay? And then if we continue, if we go to 32K, our latency maintain kind of almost constant, right? Because we take a snapshot, the KV cache, the size stay the same, right? No matter how long your input length is, right? So that's why our latency stay the same. But then for the baseline, it's already run into out of memory error. Okay, so that's what this line is showing, and then it doesn't have a green square anymore, right? Okay, and then here are some comparison across different data sets, right? 16 of them. And compared to the previous state of the art, it's called H2O, right? Then you can see H2O is also like KV compression. They keep 4096 tokens, right? And we can keep either 1024 or 2048, right? So you can actually design that. And then typically the bold font represent the best result, right? So typically you can see we can beat H2O. And then the top one is RKV, right? And then interestingly, sometimes Snap KV can even outperform the RKV case, which is also kind of understandable, right? So if you are reading a very long article, and a lot of times the key message just got diluted, right? So if you can really extract the most important tokens, only pay attention to those, sometimes you can even have a better result, right? So that's what these results are showing. And then here, this is an interesting study. So this is like a needle in a haystack study, right? You challenge the model to accurately retrieve information from specific sentence. It's called needle. Concealed within an extensive document, the haystack with a sentence placed at a random location. So without Snap KV, it's basically the baseline just run out of memory at 33K here, right? But with Snap KV, we can run without any quality drop up to 140K, right? And then beyond 140K, sometimes we have some accuracy loss, right? So minor accuracy loss. but then we can go all the way up to 380K, right? So this is another interesting study, right? So it can achieve up to 380x compression ratio because the KV cache we have is 1,000, we only have 1,000 KV items. And then here we can handle 380,000 input lengths, right? So that's 380x compression ratio. Okay, so, all right, 3 minutes. So one promising direction. So our ADD design, right? So I don't know whether you guys pay attention to this new conference. So actually, our colleague and your former colleague, right? So IBM VP Ruchir Puri and I, we co-founded this AD design, right? It was a workshop in 2024 and become a conference this year, right? We call it IAD, right? Because it represents a young and growing energetic boy, right? And so here, from the AD design point of view, right? I propose some directions. Maybe some of the students are interested. For example, AD the debugging for HelloSense RTL code, right? So this picture is interesting. You have a bug, right? That's a caterpillar, okay? So we run into all kinds of bugs, whether it's HelloSense or RTL, right? Verilog, okay? And then here, we create a so-called Chrysalis dataset. It has the bug-free code and some buggy code. The buggy code is inserted by large language models. And then we have some ways to validate the bugs are inserted correctly and all that, right? So you have the ground truth, you have the buggy code. You can use that data set to fine-tune a kind of a co-pilot thing, right? The large language model can be a debugger for you, okay? And so then after the debug, you have a beautiful butterfly coming out, right? So that's the life cycle. So right now we are building that butterfly, okay? So stay tuned. And then formal verification and also our AD design automation, right? So I will skip the details. And then conclusion, A3C3, effective design methodology, right? So I think the keyword is algorithm, hardware, co-design. We are familiar with co-design, but also co-search and co-generation, right? And then suitable for adaptive, evolvable AI algorithm accelerator development, right? Through we produce Sky9, EDD, etc. And then extension to hardware-aware ORM optimization, right? An exciting research direction, right? Hopefully will extend it into other scenarios like a distributed KV cache, right? PGA GPU, SmartNIC, heterogeneous computing, or in the future, even quantum computing and all that. So I hope the message is the journey has just begun. Okay. So it's a methodology, right? Let's keep going. Yeah. Thank you very much. And I want to acknowledge right, all the funding resources, including the C3SR, right, that I mentioned at the beginning, and then now you become IBM Discovery Accelerator Institute. Yeah, be happy to answer questions.
Yeah, questions.
Did you also consider in-memory computing in the selection process?
Oh yeah, so great question. So not yet, and I think.
Because it can be combined with
yeah,
some of your techniques.
Exactly.
Even better.
Exactly. I think in-memory computing is quite important. Actually, we just had an ASF workshop, right? Jinjun was there as well. And it's AI plus hardware for 2035, right? Shaping the next decade. And then AI embedded into memory. That's another type of AI hardware co-design. Right, so quite interesting, but also quite intriguing, right? So based on the existing study, so people of course demonstrate you can do logic and all that on top of memory, but then overall density can degrade by 100x. Right? Originally, have very dense memory. Now with logic embedded, suddenly become very sparse. Then it's another underutilization kind of issue. How do we explore? Yeah, it's a
Varsity also.
Yeah, exactly. Yeah.
By the way, do you have summary of that workshop yet?
We are still writing the.
Well, yeah, we're writing a vision paper for that, right? Yeah. Mhm.
I talked to Raj and he also said it would be.
Yeah.
Thanks.
Yeah.
Thank you.
Great question. Yeah.
Any other questions? Here we go.
Yeah.
Thanks, Dr. Chen, for the great talk.
Thank you.
I have one question related to the conventional wisdom in the computer architecture and computing. I wonder, in your perspective, right now, in the LLM era, what's the bottleneck or boundary of the computing system and the AI models? It is because when I was students, we are talking about it's ALU bounded, and later on people say computing is memory bounded, and then later on become the IO bounded. I just curious, what's your thoughts on the future LLM or large language model for the computation? What's the bottleneck?
Yeah. Another great question. I think it's energy bounded. Now it's a power wall issue, right? And so actually we were chatting right today, right? And one key limiter become actually power supply, right? So if we think about all this huge LLM coming out, right? And whether it's inferencing, whether it's training, right? And the power just it becomes so power hungry, okay? And then actually US is kind of falling behind, right? So that's why there are so many different discussions whether these smaller scale nuclear kind of power sources will need to be revived and right and things like that, right? And then if we look into the large language model or any computation intensive workload, data movement become dominating, right? Based on some Google study, right? Sometimes the data movement takes 90% of the energy, right? Or latency, right? Compared to the computation itself, right? So that's again, right? Near memory or in-memory computing or 3D integration, all those are great kind of promising directions for the future. But overall, energy efficiency can become a huge challenge. That's also a very promising research direction. Yeah. Okay.
Any other questions? Actually, for the students, you can see actually the work Professor Chen did, right? And both the Sun and the Snap and the KB. These are technologies behind like a lot of the LLM you are using. Why it becomes faster, right? And the throughput and some of the technologies has already been adopted. So a lot of the research actually that's how we push the state of the art forward. So.
Right. So right now I can give you an update what we are doing now. We are doing vision transformers for like a speculative decoding, right? Similar to Medusa, but for the vision transformers, it's kind of different. And it can be transformer or it can be diffusion models, right? So those, for transformer, then you are also talking about token, but these are the little pictures, right? Patches, right? So you partition the picture into small patches, right? Each patch is a token, but then those tokens are quite interesting. they are not words, right? For example, some tokens are totally similar if it's a background, right? So then there are some other idea that how do you really predict those tokens and right? So we are also doing compression for vision transformer, right? So stay tuned, right? Hopefully we can release some new results soon. Yeah.
You recently did some of the automation, how to automatically map the large language model to the FPGAs as well.
Oh yeah, right, yeah.
Very interesting recent one.
Right, yeah. Okay, I have no time to talk about that one today. Yeah.
Okay. So I think any questions online? Anyone? I know where we Zoom. Any questions? No? We don't. Okay.
Okay. All right.
So now I think we're leaving, okay, 8 minutes past the time, so 6 minutes, okay, so.
Yeah.
Let's give, thanks, Professor Chen's wonderful talk.
Yeah.
Yes. Thank you.
Yeah, thank you very much.